The idea of humanity becoming a multi-planetary species has long captivated the imagination, a vision of a future where our destiny is not confined to a single world. At the forefront of this ambitious pursuit stands Elon Musk with his company SpaceX, championing a bold plan to establish a self-sustaining city on Mars. This grand aspiration, however, raises a fundamental question. Is Elon's plan for Mars truly possible? SpaceX's vision hinges on the development and mass production of Starship, a fully reusable super heavy-lift launch vehicle. The core concept behind Starship is to drastically reduce the cost of space travel by making rockets as reusable as airplanes. Starship is designed to carry both cargo and up to 100 people per flight, a capacity far exceeding any previous spacecraft. The sheer scale of this vehicle, combined with its reusability, is intended to enable the transport of millions of tons of cargo and 1 million people to Mars over time, a critical step towards building a self-sufficient Martian city. The motivation behind this endeavor extends beyond mere exploration. It is rooted in the belief that becoming multi-planetary is essential for the long-term survival of humanity. A catastrophic event on Earth, whether natural or man-made, could threaten our existence, and a self-sustaining outpost on another planet could serve as a vital safeguard. Beyond survival, the prospect of expanding human civilization, unlocking new scientific discoveries, and pushing the boundaries of what is possible fuels this ambitious goal. However, the path to Mars is fraught with immense technical challenges, beginning with the journey itself. Launching a vehicle as massive as Starship, especially with the frequency required for colonization, demands unprecedented reliability and efficiency. A key innovation for interplanetary travel is orbital refueling, where Starship would be refilled with propellant in low Earth orbit by other Starship tanker vehicles before embarking on its journey to Mars. This complex maneuver, akin to aerial refueling for aircraft but in space, has never been done before with rockets, and is crucial for enabling Starship to carry significant payloads to Mars. SpaceX aims to demonstrate this capability in the near future. Once en route, the long transit to Mars, averaging around 115 days, presents its own set of hurdles. The Martian atmosphere, though present, is extremely thin, about 100 times thinner than Earth's, and primarily composed of carbon dioxide. This thin atmosphere makes aerodynamic deceleration and precise landing of large payloads incredibly challenging. Starship is designed to enter Mars's atmosphere at high speeds and decelerate aerodynamically, but the harsh conditions, including atomic oxygen, will test the vehicle's heat shield to its limits. Beyond the technicalities of getting there, establishing a foothold on Mars introduces a new array of difficulties. Building initial habitats that can withstand the extreme Martian environment, with temperatures fluctuating wildly between 70 and 0 degrees Celsius, and a toxic, unbreathable atmosphere, is a monumental task. Power generation on Mars, especially during dust storms that can block out the sun, requires robust and reliable systems, potentially relying on nuclear sources. A critical aspect of long-term settlement is in situ resource utilization, or ISRU. This involves using local Martian resources to produce essentials like water, oxygen, and even rocket propellant, reducing the reliance on costly resupply missions from Earth. For instance, the Sabatier reaction can be used to produce methane and oxygen from Martian atmospheric carbon dioxide and water ice, which could then fuel return journeys. NASA's MOXIE experiment on the Perseverance rover has already demonstrated the ability to produce oxygen from the Martian atmosphere, a promising step for ISRU. However, the full-scale implementation of ISRU for a self-sustaining colony remains a significant engineering challenge. The human element introduces perhaps the most profound challenges. The physiological and psychological impacts of long-duration space travel and living in an isolated, hostile environment are considerable. Astronauts on a Mars mission would be exposed to significantly higher levels of radiation from galactic cosmic rays and solar particles due to Mars' lack of a global magnetic field and thin atmosphere. This radiation exposure increases the risk of cancer, damage to the central nervous system, and other health problems. Some experts suggest that without major breakthroughs in radiation shielding, a Mars mission could carry a mortality rate of up to 50%. Furthermore, the reduced gravity on Mars, about 38% of Earth's, could lead to bone and muscle weakening, and its long-term effects on human health, especially for children born on Mars, are largely unknown. The psychological toll of isolation, confinement, and the immense distance from Earth also requires careful consideration. New protocols for assessing crew's psychological health and maintaining well-being would be essential. The long-term vision of terraforming Mars, altering its atmosphere and surface conditions to make it more Earth-like, is a concept often associated with Mars colonization. While captivating, this is a highly speculative and incredibly long-term endeavor, spanning centuries or even millennia, and is not a prerequisite for initial human settlement. Beyond the technical and biological hurdles, the financial and economic feasibility of establishing a Martian city is staggering. Estimates for colonizing Mars range from hundreds of billions to trillions of dollars. Elon Musk himself has acknowledged the astronomical cost, stating that building a Martian city could require over $1,000 trillion, far exceeding current global GDPs. While he believes a 1,000-fold improvement in rocket technology could reduce the cost significantly, funding such an immense undertaking will require unprecedented levels of investment, likely a combination of private and public capital. The economic model for a self-sustaining Martian colony, including how it would generate value and become independent of Earth's resources, is still largely theoretical. Moreover, the regulatory and ethical landscape of Mars colonization is complex. The Outer Space Treaty, a foundational international agreement, stipulates that outer space, including Mars, is not subject to national appropriation and should be explored for the benefit of all countries. This means no single nation or private entity can claim sovereignty over Martian territory. The legal status of a self-governing Martian colony and the rights and responsibilities of its inhabitants under international law are yet to be fully defined. Ethical considerations also arise regarding planetary protection, preventing contamination of Mars with Earth microbes, and the long-term implications of human settlement on another celestial body. Despite these formidable challenges, the drive to explore and expand remains a powerful human impulse. SpaceX's iterative approach, with continuous testing and development of Starship, aims to address these issues incrementally. The company plans to send uncrewed starships to Mars in the coming years to gather critical data on entry and landing, serving as precursors for future crewed missions. The goal is to lay the groundwork for a permanent human presence, surveying resources, preparing landing surfaces, and setting up power generation and habitats. So, is Elon's plan for Mars possible? The answer is nuanced. The vision of a self-sustaining city on Mars within a few decades, while incredibly ambitious, faces immense scientific, engineering, biological, and economic obstacles that are far from solved. Many of the technologies and systems required are still in their early stages of development, or have yet to be proven at the scale necessary for colonization. The challenges are not merely incremental improvements, but often require fundamental breakthroughs. However, possibility is not a binary state, but a spectrum. The history of space exploration is replete with achievements once deemed impossible. The sheer audacity of the vision, coupled with the rapid pace of innovation in private space ventures, suggests that progress, perhaps slower and more arduous than some timelines suggest, is indeed achievable. The question may not be if humanity will reach Mars, but when, and under what conditions. The journey will undoubtedly be one of the most challenging and transformative endeavors in human history, pushing the boundaries of our technological capabilities and our understanding of what it means to be a multi-planetary species. What are your thoughts on the feasibility of a self-sustaining city on Mars? Share your perspectives in the comments below. If you found this discussion insightful, consider subscribing to Skybound Minds for more explorations into the frontiers of science and space. Your engagement helps us continue to delve into these fascinating topics.